Okay, so we start the lecture. And what we have, we are going according to the plan, and our plan is very complex. So we have studied complex analysis. What have been done? Second, Fourier series. Yes. In very abstract and general form, in Hilbert spaces. Hilbert spaces. Last lecture we studied different types of convergence. Pointwise, in each pointwise, B, L2 convergence, A, B, C is uniform convergence. Uniform convergence. This is the strongest. This is the strongest. And it implies both this. So if you have uniform convergence, we are fine. We can do everything. These convergences do not imply this. And you should have counterexamples in your head. Also, you can try to propose your own counterexamples, not only copy mine. And these are also not, there is no relation that this implies this or this implies this. But what is good, because pointwise convergence is typically easy to prove, which we Lebesgue theorem, that if for any x, fnx converge to fx, and all of them are majorated by the same function, and this function is integrable, it's non-negative because this non-negative is less than infinity. Then we can change, then pointwise convergence imply integral convergence, and limit of integrals. I don't write here, it's maybe from AB or from minus to plus infinity fnx dx. We can put the limit into integral and get integral fnx, it's go to fx limit and go to infinity fnx dx, which is fx. This is fx. So there is some way go from pointwise convergence to convergence of integrals, in particular to L2 convergence. So we studied three part of the course, and coming fourth part of the course, we should continue. Also, it is maybe quite eclectic, so many things in one course. So we should go to part 4, which is Fourier transform. Fourier transform. Fourier transform we also will do in very abstract and general form, which is include a bit about theory of distributions. And then will be just 5. The last part will be Laplace transform. Laplace transform is similar to Fourier transform, but there's some differences between Fourier and Laplace. In some way, it is even maybe not good, because you try to work with Laplace as Fourier, but there is a difference, and sometimes students miss this difference. Okay, so now this part 4 of our course. Fourier transform. Okay, so now we destroy everything and put our blackboard as good as possible. Then we destroy this and go to Fourier transform. Fourier transform is a kind of generalization of Fourier series for non-periodic functions. So we call Fourier series. So we have fx. Suppose it's converged. Let us write in this form n plus n from 1 to infinity an cosinus nx plus bn sinus nx. If we use the Euler formula for sinus and cosinus, we can write fx in complex form to be summed plus infinity cn en x. Cn now complex coefficients. Cn now complex. And function, this function is periodic. Function which is expanded in this form is periodic. So if we have the exponent en x plus 2 pi is equal exponent en x multiplied 2 pi n, and this is 1. This is 1. So all these functions are periodic with period t equal to pi. With period equal to pi. And coefficients are given by integrals. Cn is equal, we multiply both parts by, so we get, how to get Cn. I multiply both parts for this with sign minus, yeah? So I get that it is integral, this is integral from minus pi to pi. Here would be fx minus, that they would destroy each other, enx dx. And we need normalization. Normalization would be given by integral from minus pi to pi when we integrate 1. So 1 is enx multiplied now en minus x dx. So normalization is 2 pi, so 1 over 2 pi. 1 over 2 pi. So this is complex Fourier series. No, Fourier series is more or less calculation of integrals. So to find coefficients Cn, you multiply fx by this exponent. If you are lucky, you can integrate, and you find these coefficients and write Fourier series. In very, very often in many applications to signal analysis, wireless communication, it's enough. Signals are typically periodic. Yeah. Now, suppose each signal is not periodic, yeah? So we cannot hope that there is period. So we cannot write in this form. So we cannot use this. What then we should do? Then we should integrate this from minus infinity to plus infinity. From minus infinity to plus infinity. And of course, we can use another sign and so on. So this was the ideal Fourier transform. So the ideal Fourier transform, if fx is not periodic, then integrate from minus infinity to plus infinity. So that's all. Then we will get something similar to arbitrary signals. Now we're coming to formal definition. We forget about Fourier series. And we define Fourier transform, motivated by this definition of Fourier series. So, definition. Let f belong to the space L1 minus infinity plus infinity. This means that integral from minus to plus infinity fx dx is less than infinity. So function which is integrable with its absolute value. Then we define this Fourier transform. Then the starting to finish. Then f of f in the point y is given. Sometimes it's also f tilde y is given 1 square root of 2 pi integral fx ex y dx. By analogy with Fourier transform, I should write here minus, but it's okay. There exist people who write here minus. And I should make remark about different definitions of Fourier transform. So, first of all, it could be different in different books. You can write different, but the theory is the same. Definitions. So one definition is you write, don't be afraid if you need minus xy dx. And the second here can be instead of 1 of p, it could be 1 over 2 pi. Either this or both this. What is a bit worse, in some book, people use this definition. 2 pi here, xy dx I. And here also, and here now no coefficient at all. No coefficient. At all. So you can meet different sorts of definitions. This is not so nice since here is 2 pi in the exponent, but then there is no any coefficient in front of integral. No coefficient in front of integral. So in any event, this is our definition which we shall use. Our definition which we shall use. Of course, this function is also integrable because absolute value of this exponent is 1. Absolute value of exponent is 1. Multiplication by this exponent does not change anything. Okay, now let us start to study first formal properties of Fourier transform without thinking about convergence of integral, not convergence. So we can write formal properties. Formal properties. For example, I would like to find derivative of this function, d f tilde dy in the point y. So I would like to find some good formula for Fourier transform, for derivative of Fourier transform. If I look to this integral, I integrate this variable x. So variable y is parameter. So it's not related to integral. So I can take derivatives if everything converges inside the integral. This is constant with respect to y, and this function depends on y only on this place. So the result would be just derivative of this function, so y, and here is integral from minus infinity plus infinity. If I derivate this function, it's itself multiplied by this ex, fx, exy dx. So we can write in the terms of operator f, the Fourier transform df f dy is equal. So it is again Fourier transform, but of these functions. So I can take away, and here would be Fourier transform of function x f. So this is the first formula, which we start to construct what people call operational calculus for Fourier transform. So if we differentiate Fourier transform, is the same as take Fourier transform of f multiplied by variable. F multiplied by variable. Now, if we continue this business, differentiate many times, what we shall get? We differentiate many times, we get this formula, dn dyn f equal, so it appears I in the degree n, f xn f. So this is basic formula of the calculus of Fourier transform. So if you want to calculate derivative of degree n of Fourier transform, we will get this formula. Let us denote it star one. In parallel, we develop first formal calculus. In parallel, we're starting to think to what class of functions we should define Fourier transform to get a good calculus. So to be able to differentiate Fourier transform, we should be able to define Fourier transform at xn multiplied by f. So this fourth formula is valid. The validity of this formula, to be able to differentiate Fourier transform, to be able to find the derivatives of f, we should assume that xn f belong to L1 for any n. The function f multiplied by any monomial should be integrable. So in particular, this means that if we multiply f, for example, 1 plus xn, 1 is give us f with zero derivative. If we multiply our function and by this absolute value, fx, it should be bounded. So this function in particular should be bounded for any n. Should be less some constant Cn less than infinity. So our function should decrease very quickly. So to be able to differentiate Fourier transform, we want this function decrease quicker in any degree of x for any n. So if you want to have the Fourier transform is infinitely differentiable, we should assume that our function decrease very quickly. Okay. Now, suppose now we would like to derive second formula. Now, suppose that all derivatives of our functions are integrable. Suppose for this formula we should preserve. This formula with okay, it will be okay. So we have here place. Now I want to integrate. I want to, for example, I have Fourier transform of derivatives of f. Yeah. So it is what is Fourier transform of derivatives of f. First it was derivative of Fourier transform. Now Fourier transform of derivative. Yeah. And here is integral f prime x e xy dx. Yeah. No, somewhere from course and analysis, you have such idea. If you see in some integral derivative of function, even without thinking about anything, put it into differential, and then make integration by part. So, okay, we destroy the basic formula. Maybe not so good, but it's okay. So it is equal 1 to pi integral exy dfx. And now I want to integrate by parts. So it would be 1 square pi. Here would be fx exy from minus infinity to plus infinity, and minus and derivative of this function with respect to x minus, it would be I and y, but y is not integration variable. Y is constant for this integral. So y can be go out from integral. Yeah. And here's again fx exy dx. Yeah. So nothing special, just integration by parts. Now, we want that this term will disappear, this term will disappear. And it's really the case, because if f is, we know that f is in L1, so it is integrable. It implies that fx should go to 0, x go to plus minus infinity. Because if function does not go to 0, if it's unbounded, if it's not going to 0, then its integral is infinite. So this term disappears because of this condition. And we get the second formula. And who is this? This is minus I multiplied by y, and here's Fourier transform of f. So Fourier transform of derivative in the point y is equal minus ey, and here is Fourier transform of f in the point y. So if you want to find Fourier transform of derivative, we just multiply Fourier transform by I variable. This is sometimes x and y are called conjugate variables. If x in applications, if x again time t, then Y is energy, is E energy. So by going to Fourier transform, we can get understanding at what frequency, or it's better frequency, but frequency is related to energy. Yeah, frequency. So by calculating Fourier transform, we know at what frequencies our signal is the strongest. So the absolute value Fy is the amplitude of our signal on frequency Y. And people do this in mobile communications. Of course, it's computer programs who calculate Fourier transform. But nevertheless, you have some signal. In time, it's maybe some very noisy. Then you take Fourier transform, and you see that for some interval around some y0, in fact, in the Fourier domain, it is very strong spike. Then we understand that in fact signal is going on this frequency, and the rest is more or less noise. And when you want to send, for example, how work your mobiles, they typically just select this frequency and send signal on this frequency by taking away noise. For example, there exist resenders. Yeah, so we send signal to one station, then it sends further. And in the process, when it goes between two stations, there's noise. And these stations, they make Fourier transform. They don't want to send noise further. They make Fourier transform. They take, oh, our signal is like this. Then it's possible to make inverse Fourier transform. We shall come to this back. So if you now know Fourier transform, you can find signal, and then they say clean it signal to further station. They say gain noise and so on. So where we are here, and we are here. Now, of course, I want to repeat this many times to take Fourier transform of derivative of degree n. And I get the second basic formula. That if I take Fourier transform of derivatives of the order n in the point y, what it would be? At each step, I generate this multiplication and Fourier transform of f. So this is the second basic formula. Second basic formula. Now, to be able to do this, we also want that any degree of any derivative of f should be integrable, and it's go to 0 on infinity. So it would be very good if you have the same inequality to any derivative. So if for any derivative you have the same inequality, we can do what we want. Differentiate Fourier transform or find Fourier transform of derivative. So we guess that good class of functions. For this Fourier transform calculus is class of functions which satisfy such things. So for any n of m, we have such an equality. Derivative of degree n x is less or equal some constant Cnm, and here is polynomial of degree m. So our functions decrease very quickly, quicker than any polynomial. And any derivatives also decrease very quickly, quicker than any polynomial. denote this inequality. This is, for example, star 2, and this just star. Denote this inequality by star and consider class of functions which satisfy these inequalities for any n and m. Denote the class of such functions S of R. Or sometimes I just write simply S. So this space was suggested by French mathematician Laurent Schwartz. And this is more or less the good domain of definition of Fourier transform. These very quickly decreasing functions. And we can formulate theorem. We shall not prove it because it's again very, very, very long technical proof, which is you will not get anything new in ideas, but nevertheless, it's good to formulate theorem f from S to S is how called injection, surjection, bijection. So it is 1-to-1 and on this space. So Fourier transform of any function from S is again function of this type. And it is any function of this type is the image of some function from this space. Now, in particular, this theorem tells that even Fourier transform satisfies star. So even if y as function of y satisfies star as a function of y. So this space is great because f and its Fourier transform have the same properties. They very quickly decrease jointly with all derivatives. In many books, the space is called the space of quickly decreasing functions. Space of quickly decreasing functions. Space of quickly decreasing functions. It's space very nice, but it is maybe too small. So first question, are there such functions at all? What is function which decrease so quickly? With all its derivatives. Basic example. Maybe I put this formula somewhere in where it is visible. It is visible here. And destroy it. So Fn is equal minus Ey n f, and Fn derivatives of f is equal I n f xn f. So these formulas now here because we shall use them. Now we can destroy everything. What I want to do now, I want to calculate Fourier transform of one very important function. And I hope that I will do this. I'm not so good with integrals, but nevertheless. So consider function fx, which is e minus x squared divided by 2. So this is in probability theory what is called Gaussian Gaussian distribution. Gaussian distribution. If you study probability theory, this is a kind of bell, very quickly decreasing. And typically, if you have some very big ensemble, so it is concentrated near, it's typically mean value of this ensemble. So in our case, mean value is 0. So this is Gaussian distribution, and majority of big statistics follow this distribution. So a lot around mean value, and then it's very quickly decreasing. So this function is, of course, from this space, because if you multiply this, because exponent decrease quicker than any polynomial. If you multiply exponent minus x squared by polynomial, the limit is always 0. The limit is always 0. If we try to, because 1 plus x m go to 0 for x plus minus infinity for any m. Because exponent is stronger decreasing than increasing of any polynomial. If you start to differentiate it, it will appear polynomials in front. So, for example, let's consider the first derivative. Minus x. So this function is again, its main decreasing factor is again the same. So appearance of polynomial does not change anything. So derivative also decrease quicker than any polynomial. So derivative is also decreasing quicker than any polynomial. And the same is if we differentiate one more time, it would be another polynomial and so on. So f n x goes to multiplied by go to 0, x go plus minus infinity. Maybe we need not absolute value, but okay. So this function, real example of function from S. And if you multiply this function by any polynomial, it's again in S. So if we write such function, it's also in S. And if you take linear combination, so no, I want to tell that S contains many functions. But of course, the problem with these functions is they should decrease. They should decrease very quickly. Therefore, later we should think how to extend the class of functions where we can define Fourier transform. It is good class, very good class because of this property, but it is too small. It is too small. It is too small. Okay, so let us try to find this Fourier transform. Let us try to find this Fourier transform. Just we should calculate integral. We should calculate integral. But first I want to find just the integral from minus infinity to plus infinity, x squared divided by 2 dx. This we would need in the process of calculation. There are many ways to calculate it. If I remember correctly from when I was student, we did the following. Instead of this integral, denote it by I. We considered I multiplied by I. Very strange trick, but it works. So it would be maybe it's not good to use y because it would be, let us try here x1 and here x2. Squared divided by 2 dx2. So now we unify these integrals. We are on the plane. we are on the plane, x1 square plus x2 square divided by 2, dx1, dx2. And then we introduce polar coordinates, yes? So x1 radius, I think cosinus theta, x2 radius sinus theta. And then in polar coordinates, again, if I remember correctly, it would be r d theta. Or I think it's correct, yeah? Yeah, good. So now, who is this? This is r square, and we go to polar coordinate. It would be integral from 0 to pi d theta, integral from minus infinity to infinity, e minus r square divided by 2, and r dr. We are practically calculated it. So it gives to pi, gives to pi, and here is r going here, so it would be integral from minus, here is integral from 0 to infinity, yeah, because I is from 0 to infinity. So it would be integral exponent minus new variable, for example, z dr square divided by 2. So I think half disappeared, huh? If you have, yeah. So it would be minus z dz. If I'm correct, if there should not be 2 somewhere. From 0 to infinity. And the second integral, what it gives us, here is 2 pi. Here is 2 pi, and here is exponent minus z minus from 0 to infinity. So it gives us just 1. It is 2 pi. If there is no mistake, square of integral which we are looking for is equal to pi. It means, oh, we're too high. We're too high on the screen. So it means that square of our integral is equal to pi, and our integral is equal to square root of 2 pi. Square root of 2 pi. This trick is very useful in probability theory, because in probability theory, the integral over whole space is total probability. It should be 1. So this is not probability function. To get integral equal 1, we should normalize it. So in probability theory, if you put minus x squared divided by 2 square root of 2 pi, then integral of this function is equal px dx is equal to 1. So in function px can be considered to probability to find our system in the point x. X can be anything. It can be distribution in this space, and so it is more or less the main distribution of probability theory. So everything which is in big number, and it's starting to concentrate, no, maybe not near 0, but we can make shift. So the bell can be at some point m, which is mean value, and then it is again everything around mean value, and then very quickly decreasing. So practically all probability theory work around this, if you consider very big number of systems. So we are in fact around Fourier transform of this is called Gaussian distribution. So this Bell call it Gaussian probability distribution. And you will, if you will study statistics, probability, and so on, you will meet it many, many times. So Px is Gaussian probability density. So this is Gaussian probability density. And what we shall do now, we practically calculate the Fourier transform of Gaussian probability density. And this is very standard what you will do in probability theory later. So we are interested in this function without normalization for the moment. So f in the point y, it is we have normalization. Y is integral minus infinity to plus infinity, and here is minus x squared divided by 2 plus exy dx. So we should calculate this integral. Try to do this. I think you can do this. So this you should make change of variables. But this is square of the sum. And then you should, oh, it will be not so nice because it will be movement to complex plane. Okay, so we do this. It is not, because here is I, 1 square root of 2 pi. Of course, you will do the following. So exponent, here minus 1/2, and here x squared plus 2 I x y, and then we should make the, so here is I y till summons joins with x, yeah? So it would be plus e y square e minus e y square, yes. dx. So it would be what it would be. First of all, we look to this term. It would be square, it would be minus plus, and here is minus again. So it would be e minus 1/2 y square. Very similar of what we started. This Gaussian distribution has the properties that its Fourier transform is practically the same as itself, yeah? But what we have in integral, square root of 2 pi, here is the exponent, and here is minus 1/2, and here is x plus ey square dx. Where do we integrate? Because it's integral over complex plane. Here is x in one real line, but there is a shift to complex plane. Here is a shift to complex plane. How it look? X, y. So x is going here, but our variable, this is variable z. It's going, here is I. So it's going on this parallel line. So in fact, we want to calculate integral over this parallel line. What we do, we take as was done in our course on Fourier analysis, on complex analysis minus RR, and close the contour, and if you go, for example, go counterclockwise, integral over this rectangle contour is 0. The integral over this rectangle minus RR, IR, minus IR, of function E minus Z square divided by 2 dz is equal to 0. Because this is analytic function. So its integral is 0. Then what we have then? Integral is 0, and then we have that this integral is equal minus this integral up to these two integrals. So we have that our integral over, how we like this, over the line E x plus EY. So this line, integral over this line, yeah, E minus Z square divided by 2 dz. It's in fact equal to our integral over minus R from x R to minus R, usual real line, dx e plus 2 these integrals. Let us denote them, for example, G1 or G minus and G plus. G minus and G plus. Plus integral G minus plus integral G plus integral G plus integral G plus. These integrals are equal to each other. They have different sign because this go up and this go down. But why these integrals are equal? Because whom we integrate? Let us consider these two integrals. I hope that they're equal. For example, this integral. What is this contour? How is G plus? This contour is going in this way. It is Z, which has this form. It is x is equal to R. Here is x equal to R. Plus some EIT plus IT, and T is going from 0 to 1. T goes from 0 to 1. Maybe they're not equal. We shall see. But in any way, they disappear. They should disappear, and they will disappear. This integral minus, it is Z equal minus R plus IT, and here T goes other way around, or T goes from 1 to 0. It's better than write again minus, and T goes from 0 to 1. Minus because it goes this direction. Now, how look our function Ez on this contour? E minus Z square divided by 2. How it looks? On the first contour, it is exponent minus R plus E t square divided by 2. On the second contour, this is this is exponent minus again r minus they disappear again. They are the same, divided by 2. Here was 2 minuses, and this square destroys them. So it is the same function. It is the same function. And here we go up, and here we go down. So really, one integral plus another integral equal to 0. Great. So we use this complex analysis to calculate this integral. Our integral was here. We make closed contour. And finally, we approach these two paths disappear. They compensated each other, more or less because he is square. And then our integral over this imaginary line is equal to integral to our usual line, Go back, what we have? We have this factor. And here we can just write a real variable. And we know that this integral is equal square root of 2 pi. So square root of 2 pi disappeared. So we found the following formula. We found Fourier transform of this function. So Fourier transform divided by 2. It is again the same function. F, it is E divided by 2. Good. So Fourier transform of Gaussian function is again Gaussian function. So here it's very nice. Application of complex integration. So it is very good question for exam. Yeah, find Fourier transform of Gaussian function by using this machinery. So here is nothing very big theoretical. Yeah, very big theoretical. Okay. Now. Maybe break. Yeah, it's break. Yeah, we make break. Yeah. Okay, now it's break. Stop recording. Okay, so we continue. We finished with Fourier transform of Gaussian function. And this function, we can check this formula. For example, if you would like to find Fourier transform of x squared divided by 2, the point y. Of course, we can again put integral and work with this square exponent, but we can use this formula. It would be minus I y, and the same square divided by 2. Even if it's more difficult, for example, if you want x in the degree 100 divided by 2, if you start to calculate this integral, it will take many integration by part. But in our case, or what I did some mistake, no. It's in any event we need to calculate. If I want to find, it would be derivative. It would be derivative of this function. If I would find y, x multiplied by f, it would be first derivative divided by I. First derivative of this, it would be minus y, is correct. And yeah, so it looks so, because it was divided by I, yeah. The text is correct. This was not good idea, because in any event I should differentiate this exponent 100 times. So it does not help us, this formula, because the difficulty did not disappear. Multiplication by x in 10 leads to derivative of degree 100, and this function to differentiate 100 times, it's not easy. It's not easy. So this is the case when my idea that we can get something for free did not work. Okay. Now we want to study a different thing which would be useful in the Fourier analysis, and which is called convolution. Convolution of two functions. For the moment, no Fourier transform, but it will appear that this convolution is very useful. It's very useful for Fourier transform calculus. What we do, we take f1 and f2, both are integrable, absolutely integrable. And we define such function f, which is denoted f1 star f2 in the point y. And this is equal, or okay, so it is equal integral from minus infinity f x1 f2. So is the problem y minus x or x minus y? Let us write x minus y, or later we can change the sign if it does not work. First of all, first of all, I want to prove that this function is again in L1. So mini theorem f2 is again in L1. So it is again integrable. In particular, if I was able to have Fourier transforms of f1 and f2, I would be able to define Fourier transform of f. Okay, so let us integrate this function. Integrate fy dy. So it is less or equal integral, take absolute value, integral this dy, and here integral this, and with 1x, f2 x minus y dx, yeah, dx. Now, if let us make the change of variable. Let us denote x minus y, or no, we do a bit different thing. We change the order of integrals. It's another unconscious trick. If you see two integrals in different order, always try to change the order, and you will get something good. Let us change the order. It would be this integral dx, and here would be integral. And if f1x does not depend on y, f1x, yeah. And in second integral, we have this f2 x minus y dy. And now I would like to change variables, and now we will understand the sign at this moment. We would like to change variables. I denote x minus y by, for example, t. then dy, so y is x minus t, so dy equal minus dt. I started to be not so happy with sign, minus dt. And if I change and yeah, so if it go from minus infinity to plus infinity, minus, yeah, so t goes from plus infinity to minus, and if you change sign, oh, yeah, sign disappear, да? Sign disappear. One minus coming from differential, but since here is minus, so integral was from minus infinity to plus infinity. And so, for example, y was plus infinity, minus infinity, and t would be from plus infinity to minus infinity. Yeah, so it's different sign. So when I change the integral, it would be, yeah, so minus will disappear. So this would be just the product of two integrals. Dx, f1x, and the second integral, f2t dt. So this was less than infinity, and this was less than infinity. So the theorem is proven. So if there were two functions which were integrable, the convolution, this function is again integrable. It's again integrable. I'm still not showing the sign. We shall the sign we can change always. We should prove another theorem where we understand where sign is correct. No, another possibility is to write y minus x. Because there are good teachers who prepare to lecture and check this at home, but it's not your case, yeah. So we want to prove another theorem that this convolution is symmetric, that we can change, interchange them, and here we will understand whether the sign was correct or not. So the second theorem. The symmetry of convolution. On the symmetry of convolution. So we can change this function by their places. I suspect this maybe we should write in this way, but okay. Let us try to prove. Let us try to prove this. Let us try to prove this. Proof. This integral is in our definition f1x, f2x minus y dx. And let us change variables. I suspect, okay, so x minus y is again equal c. So dx is equal dt, and x is equal t minus y. So it would be integral. Yeah, so from minus infinity to plus infinity. F1, yeah, it's not, maybe it's good, maybe it's not so bad.
It should be to plus y. It should be to plus y. X is equal to...
Because maybe I started to do as Freud want, да? Yeah. So it is not, maybe not good. I wanted to do the sign what I need, yeah, so it would be not symmetric. Okay, so let us try again. Let us try again. This theorem does not change because it's in any event, it's absolute values and so on. Let us try now this definition. So maybe right definition is right definition. Why if we put here, not right, just we trying to prove this. We're trying to select the definition where it would produce symmetric. Suppose we write in this way. Suppose we write in this way. Y minus x, would it work? We want to get symmetry. We want to get symmetry. If we use this definition, then we gain y minus x equal t, and x would be equal y minus t. Yeah, so it would work. It would work. So we go back and make correction in the definition of this star operation. So it should be y minus x. Yeah. So the right definition is this. So the sign is this. If it is done in this way, then we do what I wanted, and I made mistake because I wanted mistake. Yeah. So I get this x. So now, is it good? Because now the sign would change it or not. No, it's again from minus to minus. Yeah, it's okay. It's again okay. Yeah, so x is this. So now dx is minus dt. And x was from minus infinity to plus infinity. Minus t would be from plus infinity to minus. So the sign would not change it. So it would be integral from minus infinity to plus infinity, f1 t, f2, and y minus t, f, and here it would be x is equal y minus t, f2 t dt, and it is what we wanted, f2, f1. Yeah, f2, f1. So convolution is symmetric. Convolution is symmetric. Now I want to find Fourier transform of convolution. I want to find Fourier transform of convolution. Okay, so let us first calculate and then formulate this theorem. So F1 star F2. And now let us introduce another variable for Fourier transform, for example, psi. So this is equal 1 square root of pi. And here is integral of this. This is function of y. And I multiply its I psi y dy. Oh. So I want to find Fourier transform of convolution. Now what we do, we again change the order of integration. 1 square root of 2 pi. Here would be integral, now integral dx, integral from minus infinity to plus infinity dx, f1x. And here would be integral now from minus infinity to plus infinity, f2 y minus x, exponent psi y dy. Oh. Now, of course, if we look to this integral, we again want to change variable y minus x. We denote by t. We denote by t. So then y is equal x plus t. And dy is equal dt. So nothing special, just play with integrals. Play with integrals. Now, what we will have after this change of variables? We will have after this change of variables, we will have 1 square root of 2 pi is integral from minus dx f1 x. And who will depend only, who will not depend on, no, okay, well, let us write one more step. Here would be f2 t, and here would be exponent x psi, and here would be x plus t dt, x plus t dt. Now, this guy, with x, integration is respect to t. This does not depend on t, so we can put it here. We practically here. Yeah. Dx f1 x psi x. And the second integral is also the same. It will be just some constant factor. Yeah. F2 t x psi t dt. So what we are doing? We're calculating Fourier transform of convolution. Yeah, we're calculating Fourier transform of convolution. So now you see this one is already Fourier transform of f1. And this one is practically Fourier transform of f2, but here you should put divide by square root of 2 pi and multiply by square root of 2 pi. So the formula would be the following one. The formula would be the following one. Here what we get, I have somewhere good pencils. We will get the following. This is Fourier transform f1. Here is practically Fourier transform of f2, but we should divide square root of 2 pi and multiply square root of 2 pi. So here would be square root of 2 pi. Square root of 2 pi. So we prove this formula that Fourier transform of convolution. Fourier transform of convolution is equal product of Fourier transforms up to constant factor. So we formulate this now as theorem. So Fourier transform f1 star f2 is equal to pi f1 f2. Yeah. So convolution give us possibility to transfer Fourier transform into product. So it more or less give us the idea that if we get product of Fourier transforms, if you go back, it would be convolution. If you go back, it would be convolution. Yeah, so it is about convolution, about Fourier transform. And now let us try to solve, let us try to study where Fourier transform is used. Where Fourier transform is used, yeah. Fourier transform is used to solve linear differential equations. Linear differential equations, yeah. So now we write the title. Application of Fourier transform. Here transform to solve linear, what is das mean da? Differential equations. This is what the aim, and Fourier was French mathematician who developed this calculus precisely to solve linear differential equations. So let us consider linear differential operator with constant coefficients. So P of x, let us be a polynomial. So A0 plus A1x plus AMXM. Now put instead of x differential operator ddx. So we get P d dx. It would be A0 plus A1 d dx plus AM dm dxm. So it is a differential operator with constant coefficients. For example, if Px is square, then P dx is just d square dx square. So this is differential operator. Now we want to find Fourier transform of differential operator acting to some function. So now we want to find Fourier transform of differential operator acting to some function. So f p d dx applied to some function f. So this is our aim. And then we shall use this construction to solve concrete differential equation. What will happen? We have this formula, that if you have derivative of degree n, it's appear this term. So it would be A0 plus A1 multiplied by minus EY plus AM multiplied by minus E in the degree n. And then Fourier transform of f. So in fact, formula is the following. If we find Fourier transforms of differential operator given by polynomial of d dx, we get the following formula: f differential operator applied to f y is equal, again, the same polynomial, but its variable would be this variable, and Fourier transform of f. So, what is the main essence of Fourier transform? The differential equation with some maybe very complex differential operator is transferred to just multiplication by this polynomial, but not of function, but it's Fourier transform. So we transfer differential calculus into algebra. And what is the typical problem which people study? It's this following problem. For example, we have such equation: f is equal to some unknown function, to some function g. So this is given, but this we want to find. How we do? We apply Fourier transform, and we get polynomial minus dy. Fourier transform f, what we are looking for, y, and this is gy. Then we can find Fourier transform of f, gy divided by this polynomial. And then we should reconstruct our function f by, if we know its Fourier transform. So to solve this equation, then we should reconstruct f by knowing its Fourier transform. Of course, this business is not so simple because this polynomial can have zeros. So this would be a function with singularities. It would be function with singularities, and we should integrate this function with singularities. It's not so easy, but in many cases it's okay without problems. So now is the question how to reconstruct f. So we come into this problem. We try to escape it as much as possible, and maybe on this we finish. Now we come to this problem. Now we want to find f if you know its Fourier transform. How can we find f if we know f of f? And it's given by inverse Fourier transform by this formula, which we'll prove later. F minus f tilde in the point x is given the following. So it is also integral with the same normalization, square root of 2 pi. Here is Fourier transform, function of y. Here is the same, but sine minus dy. So reconstruction of function, if you know its Fourier transform f tilde, is given practically by the same formula, but here is minus. If you define Fourier transform as minus, here would be plus. So in some books, these formulas are interchangeable. Or in the operator terms, we can write f minus f is equal to f. So if we apply inverse Fourier transform operator to Fourier transform, we again get our function f. And maybe if we go now back to our problem to solve differential equation, so we got this formula, and now we should find f(x). It will be solution of our equation. Just inverse Fourier transform pi of this function gy, or gy, it's not gy, because we should apply Fourier transform to both paths, yes? It was this equation. We apply Fourier transform to this path, we get this. But we also should apply to this path. So if we have two functions, for example, u equal v, then we just write fu equal fv. And here we did not apply to, so it should be, yeah, so here is g, but here should be fg. Yeah. And here also should be fg. I just forgot to apply the Fourier transform to the right-hand side. So now to go back, we take Fourier transform of g, y, divide to this polynomial, y, and here is inverse Fourier transform minus ex y dy. So this is the general formula to solve this equation, for any polynomial. Of course, typically the problem is that this integral is not easy to calculate. But since you have computers, you always can put this in computer and you will find solution by using this formula. Because this was differential equation. Of course, computer can try to solve even differential, but this is easier. You have this function, you should just integrate it, and you will get solution of this equation, So more or less, this is all what you need to know about this Fourier calculus, but we shall go in details next lecture. So the main thing is this formula. The Fourier transform of derivative is given by this formula. The second, if we apply now Fourier transform to differential operator, we just get polynomial of this variable, differential equation is transferred just algebraic equation. Fourier image of unknown function is multiplied by polynomial and equal to Fourier image of right-hand side, which is given. So we can find Fourier transform, and then we use this formula to inverse Fourier transform and to find our solution. No, I hope that we will have time and we consider concrete equations, how to solve them by using this Fourier transform method. What is typically, it's not one variable. In usual problems, there are many variables. And more or less this calculus, it works also for many variables. Here would be partial derivatives. So for partial derivatives, we have the same formula, but here would be just yg with index of coordinate. So this is very powerful calculus, even for partial differential equations. So it could be not only differential variable of one variable, but maybe of 4 or so on. Yeah, okay. So we finish for today. And if you have time, try to solve problems, those who did not do for